Okay, I'm going to show how to calculate the center of mass of a half disk. There's another video I just finished that shows you how to do that in polar coordinates. In this video, I'm going to show you how you can do it in Cartesian coordinates, and they give you the same result, which is, of course, reassuring. So when we talk about slicing things up in polar coordinates, we made concentric rings on this. If I want to do this integration in Cartesian coordinates, I'm going to slice up my half disk into little pieces like this. Okay, and slice them up. And then each of these I would cut up in little pieces and sum them up this way. So I need to know what is the volume that one of these little elements would occupy. Okay, so it's a little bit easier when we're doing it in Cartesian coordinates. So again, just remember that what we're going for here is the y center of mass. The x center of mass we can look at just by symmetry and say that there's an equal amount on the left side as the right side, and so the position of my center of mass in the x direction must be 0. Okay, the y center of mass is going to be the integral of all my little mass elements times their y coordinate, and then I'm going to divide by the integral, right, or the sum of every little chunk that I cut up and add it back up, and this at the end, right, will give me just the total mass of the object. Oops, that's terrible. So that's just my total mass. Okay. So then I need to know what is my expression for the mass element dm. So in general, right, my mass element will be the density of the object, rho, times whatever my little piece of volume is. And the volume in Cartesian coordinates is a little easier than in cylindrical coordinates, but again, it depends on the problem, right? Sometimes you definitely want to work in cylindrical or polar coordinates. But so in Cartesian, my volume element is just dx, dy, dz. So remember that this has like a thickness just of in the z direction, which would be into the screen here, of just has a thickness of t. Okay. All right, so we're going to assume this is uniform density. Again, if it's not uniform density, you can't pull this out as a constant in the integration. Okay, so then the more challenging part of doing it in Cartesian, right, is to getting the limits of the integration correctly. So in the z direction, right, so if we just draw this like, what this might look like in the, if that's my z-axis, and I just took like a side view of this disk, it goes out to some thickness t, right? So my integration in the z direction will be from 0 to t. Okay, in my y direction, since I'm slicing it up in these little strips that are parallel to the x-axis, my y integration limits are going to be from 0 to r, where r is the thickness of the disk, or the radius of the disk. Okay, so then the one that's challenging is to get the limits of the x integration correctly, right? So I want to start from here, let's say, on this little slice and end up here. But if I move further down, I need my x to start here and end there. And then, of course, at the bottom, I would need to be at negative r and go all the way to r for my last little ring slice that I'm integrating. So how do we describe what that relationship is between, what this, basically the perimeter of the disk is going to be? So if we're looking at it in this view, remember that it's just this, basically looks like a circle in this perspective, right? So y squared plus x squared equals r squared. And so my x I can at least talk about in terms of y is going to be the square root of r squared minus y squared. Okay, so for a particular value, wherever I am in my y coordinate, I want to integrate from r squared minus that y squared, right, to r squared to plus the square root of r squared minus y squared in the other direction. Okay, so let's set up the integral then. So again, just focusing on first the top part of the center of mass expression. So dm times y. And so I'm going to pull out, well, let's just put it in here first. So we'll do 0 to t in the z direction. And then we're going to do 0 to r, the radius of the disk, in the y direction. And then in the x direction, I have to integrate from negative r squared minus y squared to positive r squared minus y squared square root. Okay, and then so dx dy dz is my volume element, and then of course I still need to multiply by the density, right? Because dm is density times my volume element. Okay, and then we also need our y position. And so that's in there, and in this case, it's just y. Right? Nothing fancy there. Okay. So density is a constant in this case, so I can pull it outside the integration. We can't do that if it's not a constant. 0 to t dz, 0 to r. I'm going to bring my y in with the y integration, y dy. And then I am left with my dx, and I'm just going to put my limits there. Okay, so if I do my x integration first, the integral of dx is just x, and I need to evaluate between negative r squared minus y squared and the square root of r squared minus y squared. And then I still have all the rest of this coming down on the left side. And if I evaluate this, right, I get the square root of r squared minus y squared minus a negative of this, and so I actually get 2 r squared minus y squared. Okay, and then I'm still left with the integral from 0 to r of y dy, and the integral from 0 to t of dz. And my density's out there. Okay, I might just want to do my dz integration just so I don't have to keep writing that. So the integral of dz is just z. I'm going to evaluate between 0 and t, the thickness of the disk. And so that gives me t minus 0, which is just t. Okay, so then I can rewrite my integration of dm times y. And it is the density, and then I have my thickness t, and I'm still left with my integral with respect to y. Oh, let me bring the 2 out of there too. Okay, so there's 2. Oh, you know what? I'm not going to do that. We need it. We need it in that integration. Okay. So I still have that. I have 2 times the square root of r squared minus y squared, and then I have y dy. Okay, so setting up the integral is a little bit easier in Cartesian coordinates, but the integral itself is harder, right? Whereas when we did it in cylindrical coordinates, maybe getting the volume element until you're comfortable with that is a little bit more challenging, but the integral itself was really easy. Okay, so I'm going to do a u substitution to try and solve this. I'm going to say u is r squared minus y squared, and my du would be negative 2y dy. Okay, and when I do this substitution, I also need to adjust the limits of my integration. So I just want to make a little table here for my y value, and then what u would be. Okay, so my limits of the integration for y are going from 0 to r. So if I plug in 0 for y, then u would be r squared. And if I plug in r for y, then u would be 0. So when I make my substitution, I have to be careful and change the limits of the integration. Okay, so when I do that then, so let's just look again how this all works out, right? Because 2y dy is my du term, and then I have basically the square root of u left. So when I swap my variables, I'm going to go from r squared to 0, and then I have the square root of u du. Okay, and I need this negative term, right? I need to not ignore that because I actually only had 2y dy, so I got to put a negative term out, negative sign out in front of my integration there. Okay, so this is, u to the 1/2. So if I do the integral of that, I get negative u to the 3/2 divided by 3/2. And I'm going to evaluate between r squared and 0. Okay, so my 3/2 flips over, so I get negative 2/3 u to the 3/2 between r squared and 0. So let's evaluate that now. When I plug in 0, I just get 0. When I plug in r squared for u, then I have r squared raised to the 3/2. So multiply those together, right? So 2 to the 3/2, I get r cubed left. And a negative sign in front of that. And then out in front, I still have my 2/3 and the negative sign from when I did my u substitution. Okay, so then that y integration is 2/3 r cubed. Okay, so let's go back up because I dropped everything else that was there. So I need to bring down this part, right, the rho and my thickness t. So I get that the integral of mass times position is rho t 2/3 r cubed. Okay, and again, this is a constant density disk, so the density we can just kind of figure out geometrically is the mass divided by the volume of a little cylinder, right? If it was just a little cylinder like this, right? This face would be pi r squared, and then we would multiply by the height. So the for a general cylinder, right, it's pi r squared times our height, which in this case is the thickness t. And again, we're just doing a half of it, right? We're cutting it in half down the middle, so we have a 1/2 power. So that's my volume. So I'm going to put that in up here, 1/2 pi r squared times t. Okay, and now I plug in rho into my y coordinate for the center of mass, and so I have a 1/2 pi, no, that goes in the bottom, sorry. For rho, I have the mass divided by 1/2 pi r squared times the thickness t. I have my t term that comes down from above, and then from my y integration, I have 2/3 r cubed. So the r squared leaves 1 r left. The 1/2 flips over, so I get a 4/3. Sorry, my t's cancel out too. So 4/3 m r divided by pi. Okay, and then finally, from the y coordinate of my center of mass is going to be this integral, right? That's all the mass elements that are weighted by their y position divided by the total mass in the bottom. So 4/3 pi, 4/3 pi mass times radius divided by the mass. Remember, this is just integrating all the little bits of the piece, and so that's going to give me my total mass at the bottom. That cancels out, and so I get the y center of mass is 4/3 pi r. And so it makes sense, right? Because actually this, if we think about this is like 9-ish, so 4 divided by 9 is less than a half, and I'd expect, just from the geometry, that my center of mass, well, it should be less than 1/2 r, right? Because it's thicker down at the bottom. So that all is kind of a good reality check at the end. Okay, so you can, take a look at that. 2 different ways of doing the integration. They give you the same result, which is very encouraging. Okay, so, but also note that if the density is not constant, then we can't go pulling that out. So let's just review that, where that happened, right? So way up in the top, I took density out of the integration. If it depends on x or y or z, you cannot do that. You got to leave it in there and do the integration.